Today we continue our discussion of the vertex form of a parabola by looking at parabolas whose leading coefficients are not equal to 1. And so it'll look a lot like what we did in the last video, except for this 3 here in our example on the board. So our job is to change y equals 3x squared minus 6x minus 1 to vertex form. And completing the square, we know that we cannot complete the square when there's a coefficient in front of the x squared different than 1. What we did to complete the square to find the x-intercepts was we divided that number out. We could only do that because the other side of the equation was a 0. Because this isn't a 0, we can't divide this out. Instead, what we have to do is factor it. All right, so here's step 1. We're going to factor that 3 out of just the first two terms, okay? So 3 out of 3x squared becomes x squared. This becomes minus 2x. We're going to put the blank there as we always do for completing the square. And then this minus 1 comes outside the parentheses. So do you see how I factored the 3 out of the first two terms but not the third? Okay, so once I do that, I go back to look at the x squared minus 2x and ask myself what number completes the square, and the answer of course is 1. We've done that 100 times. Now this is where we have to be really careful, because although it looks like we've added 1 to the right side of this equation, we have actually added 3 times 1. Do you see how when we distribute that 3 to the 1, we've really added 3? So over here, what we're going to do to undo that adding 3 is we're right away going to subtract 3. All right, so here is vertex form. We're going to rewrite this as the binomial x minus 1 squared minus 4, and the vertex is 1 comma negative 4. Okay, hopefully that makes a lot of sense to you from the work we've been doing. We'll have a chance to practice that in class. All right, so now what I want to do is go through a model question that's actually number 9 in section 6.4 on page 524. This is one of your homework problems, and I thought it would be a good idea to work it through with you in this video. So here's the story. Sheila has a piece of yarn. It's 100 inches of yarn, and she wants to make a rectangle, and she wants it to be the perimeter of the rectangle. So she wants to enclose a rectangular shape with 100 inches of yarn, and here's her job. She wants the biggest possible area. And so you're probably asking yourselves, how is this in any way related to a quadratic function, right? So you're wondering, how is that possible? So if I gave you this question and told you to just go to work on it, you might decide, I'm just going to pick some numbers and see if I can't get the biggest area possible. So you might make a table. You might make a table that's got the length and the width and then the area, and pick numbers so that the 2 times the length and 2 times plus 2 times the width equals 100. So you might say, well, what about if I picked 40 for the length? So if I have 40 and 40 for each length, that means I have 20 left over for the width. So the widths would each be 10, and 40 times 10 is 400. And you might be thinking, oh, that's a pretty big rectangle. Maybe that's the shape we want. And then you might say, well, no, let's try some different numbers. Let's try 30 here. So if we use 30 for each of the lengths, then we have 60 used up here. So then the widths would be 20. And so, oh, look, we're up to 600. So that's even better. So you might get tired of this method and say, well, how would I know if I'm actually at the biggest? Until I tried every number, and that would get very tedious. So instead what we're going to do is we're going to go back to this idea of a quadratic function. All right, so we're going to look at this and we're going to assign some variables to our rectangle. So let's go ahead and call this vertical side the width. And then what we want to do is, instead of calling this the length, we don't want to call it the length, we want to call it something in relationship to the width. So we know that 2 times the length plus 2 times the width has got to equal 100. That's the perimeter formula. And so if we solve for L, right, we take 100 minus 2w, we move that over there, and divide by 2. Okay, I did that kind of quickly. You might want to pause here to see how I came up with that. And then just to make it simpler, I'm going to call the length 50 minus the w. the width. All right, so now what I have is a rectangle with a length and width dimension that have the same variable. All right, and then I go ahead and ask myself, how is it that I would find the area of this rectangle? And the answer is I multiply the length times the width, and so I would get the length is 50 minus w, the width is w, and sure enough, when I distribute that w, I get negative w squared plus 50w. And that should look to you like a quadratic equation, I hope. All right, and then I go back to the question, which is, how do I find the biggest possible area? And I might say biggest, let's see, another word for finding biggest possible area might be to maximize the area. And when I think of maximize, I think of a parabola facing down and the vertex being the maximum. So if this graph right here that I've just sketched really quickly is showing the width versus the area, then if I found the width that gave me the tallest point on this graph, I would have the width that maximizes the area. Okay, so in other words, this question is asking nothing more than find the vertex of, let's call it f of x, f of w, equals negative w squared plus 50w. So we go back to our shortcut to finding the vertex, and we take negative b over 2a, which would be negative 50 over negative 1 times 2, which would be 25 inches. And so that's the width. And if the width is 25 inches, then it turns out that the length is also 25 inches, and the maximum area we could make with 100 inches of yarn is 25 times 25, or 625 inches squared. Okay, so this is an example of a quadratic modeling problem, and we'll get a chance to practice this some more in class. All right, see you in class.